Hey guys, welcome to 2015 Level 2 Physics exam walkthrough. I'm just gonna get straight into it. Roy kicks a ball. The diagram below shows the trajectory of the ball. You may assume air resistance to be negligible. On the diagram, draw labeled arrows of appropriate length to show the following. The force on the ball at position C and at position G. The horizontal component of the velocity of the ball at position B and at position H. The vertical component of the velocity at the ball at position D and position F, okay? So, we're going to say the force on the ball at position C and position G, okay? So that's here, and here, okay? So basically the force is the weight force acting vertically downwards, okay? So that's just F, oh shoot. That's just f of g acting downwards, okay? So it's going to be an f of g acting downwards at point C, and then it's going to be an f of g acting downwards at point G. Okay, when you're drawing the arrows, make sure they're about the same size, okay? It doesn't have to be exact, but like similar size, because the mass of the ball doesn't change, and because the mass of the ball doesn't change, the weight force of the ball doesn't change, and this means that both these arrows should be approximately the same size, okay? Well, they should be the same size, but like when you're drawing them, you have to make sure that they're really close, similar size, okay? The horizontal component of the velocity of the ball at position B and position H, okay? So basically, we're gonna say that there's a VH acting on the ball at position B, and that VH is exact same as position H, because air resistance is negligible. There's actually no horizontal forces acting on the ball, and that actually means that that the horizontal component of the velocity remains constant for the entire flight. Okay, so at point B, okay, there's gonna be a V. So we're gonna label this f of g. This is going down. I'm gonna label this f of g, and it's gonna be a velocity acting horizontally. That's gonna be f. Not f. It's gonna be v h. Horizontal velocity, and it's gonna be exact same sized arrow. Okay, make sure they're about similar size. So just yeah, that's fine. At point H, so it's just gonna be a horizontal velocity acting the exact same, okay? No change, because no horizontal forces. So these the velocity of both of these is the same magnitude, okay? So we're gonna say this is v of h, okay? And it says the vertical component of velocity of the ball at position D and position F, okay? So at position D and position F, okay? So at position D, okay, the ball is still traveling upwards, okay? So you see the ball is still traveling up. Sorry, the ball is traveling up. Then it goes, go up and up and up and up. And then at E, it stops for a while. For a brief moment of time, the vertical velocity is 0. And then after the ball reaches this midpoint, it's going to start traveling down. So the vertical velocity is going to be it's going to start acting downwards, okay? So at D, the vertical velocity is acting upwards, and at F, the vertical velocity is acting downwards, okay? Okay, so we're going to say, okay, that there's a vertical velocity, I keep forgetting. There's a vertical velocity of the ball, vertical velocity of the ball acting upwards at point D, okay? What'd you say? Is this big, okay? Oh, I screwed up the arrow, sorry. Sorry, far out. It's really hard to use sometimes, I must say. Okay, so vertical velocity acting at point D is acting upwards, okay? And at point F, because it's I said it was symmetrical, no. We're gonna assume that it's symmetrical, okay? Because the points, okay? So Point D, there's a vertical velocity acting upwards, okay? And at point F, there's the same vertical velocity but acting downwards, okay? Because after point E, the ball starts traveling downwards. And because the ball starts traveling downwards, there's a vertical velocity acting downwards, okay? So that's going to be about the same size. I'll just double check. It needs to be about this. It needs to be, both of these arrows need to be the same size. So just need to make sure that this... Yeah, okay, similar. Yeah, let's just bend the arrow in the process. Alright. Oh no, this is wrong way. This is acting upwards. And this arrow is acting downwards. Yeah, sorry about the delay. These arrows are annoying. Okay, so we're gonna label this. We're just gonna label both of these vertical velocity. So VV and then VV here. Okay. So this is the merit question here. Okay. So to get a merit grade, okay, we're looking to get all of these arrows correct. To get a merit grade, okay, and that's the size of the arrows are correct as well. Okay. To get an achieved is getting 2 of the 3 correct. So you're getting the forces. So there's 3 sections, okay? So there's vertical velocity, horizontal velocity, and f of g, okay? So if you get any 2 of these, you'll get an achieved. So either 2 of these will get you an achieved. The ball is kicked with an initial velocity of 16 meters per second and an angle of 42 degrees to the ground. Calculate the initial horizontal and vertical components of the ball at position A. Position A is just at the very start. Okay, so at the very start, okay, we're going to use Pythagoras, okay, to find out Pythagoras theorem to work out the initial vertical velocity and the initial horizontal velocity. Okay. Alright, so looking at this diagram here, okay, we're just gonna draw. Okay, right angle here, okay? So we have a vertical velocity here, v of v, and then we have horizontal velocity here, which is v of h, okay? So if you're going to label this in triangle as a triangle, okay, we're going to say this is the opposite end, this is the hypotenuse, and this is adjacent, okay? So let's say we're going to find vertical velocity first, okay? So you see that's the opposite end, and we have the hypotenuse, which is given to us. The initial velocity is 16 meters per second, okay? So that's the hypotenuse, and we're trying to find the opposite, okay? So therefore, we're going to use the sine rule, okay? So we're going to say sine 42 is equal to O over h. Okay, so we know h is 16, so we can just plug in h equals 16 meters per second. We're going to say sine 42 equals to O over 16. So therefore, sine 42 multiplied by 16 equals to O. Okay, we're going to say O is vertical velocity, so we're just going to say VV equals to VV. Okay, so we're going to plug this into our calculator, okay? And you should get vertical velocity equals to 10.71 meters per second, okay? So now we're trying to find the horizontal velocity, okay? So you see here, there's an adjacent side and you have the hypotenuse, okay? So in this case, we're going to use the car rule, which is the cos rule, okay? So we're going to say cos 42 is equal to A over h. We know h is 16, so we're going to say cos 42 equals to horizontal velocity divided by 16. So therefore, cos 42 times 16 equals to horizontal velocity, okay? And if you plug that into a calculator, you should get horizontal velocity equals to 11.89 meters per second, okay? Okay, and that's basically it for this question, okay? To get an achieved, it's only an achieved question, you need both of these correct. You need the vertical velocity and you need the horizontal velocity to get an achieved grade, okay? So this is only an achieved question, okay? Moving on. State the horizontal and vertical components of the velocity of the ball at position E. Explain your answers, okay? So at position E, where is that? That's all the way at the midpoint, okay? So you know at the midpoint, okay, like I was saying, the vertical velocity is going to be 0 meters per second at the midpoint for just a fraction, like for a very small amount of time, the vertical velocity will be 0, okay? And then after the vertical velocity is 0, gravity is going to start acting downwards on the ball, and that's going to increase the vertical velocity, but now it's going to be acting downwards, okay? So when the ball is moving up, okay, there's a gravity acting downwards, so the vertical velocity gets smaller and smaller and smaller until it reaches 0 at the midpoint, and then the gravity is going to act downwards, which makes the vertical velocity act back downwards, okay? And because for horizontal velocity, you know that there are no horizontal forces acting, so therefore whatever the horizontal velocity was at the beginning will be the horizontal velocity at point E or point F. It's all the same, okay? The horizontal velocity is always going to be the same no matter where the ball is on its path, okay? It's going to be the same. Okay, so we're going to say that the vertical the vertical velocity of the ball is 0 meters per second at point B, okay? Because gravity acts this reduces the reduces the vertical velocity to 0 meters per second at the highest point. Okay, so we're gonna say that the horizontal velocity is still 11.89 meters per second. So horizontal velocity is still 11.89 meters per second, and this is because no horizontal forces are acting. Alright, and that should be your full answer here, okay? So to get, you have to state that the vertical velocity of the ball is 0 meters per second at the top, and this is because gravity acts downwards and reduces the vertical velocity to 0 meters per second at the top of the flight, okay? And you have to say that the horizontal velocity is 11.89 meters per second because there are no horizontal forces acting, and therefore the velocity remains constant, okay? So getting both these points correct is going to get you a merit grade, okay? And to get an achieved grade, you're looking at, you have to say that the vertical velocity is 0, and you have to say the horizontal velocity is constant, okay? Or you can say one correct velocity with a correct explanation, okay? So you can basically say vertical velocity is 0, horizontal velocity is constant, or one correct velocity with correct explanation, okay? So that will get you an achieved. Okay? Alright, moving on. Calculate the horizontal distance the ball travels before returning to the level from which it was kicked, okay? So if you come back here, right? It was kicked from the ground, okay? So therefore, we're just trying to figure out how long has, how far has the ball traveled, okay? How far has the ball traveled, and during its flight time, okay? Okay, so basically, okay, we know that we know the horizontal component remains constant, right? And because the horizontal component remains constant, all we have to do is figure out the total time to reach, not total time, the total time of the flight, and we can multiply the total amount of time of the flight, we can multiply that with the horizontal velocity, and that will give us the distance, okay? Because the horizontal velocity is always constant, okay? So it's only based on how much time the ball is in the air for, okay? But to do this, we have to find out what is the velocity, not velocity, how long does it take for the ball to reach the maximum height? For the ball to reach the maximum height, how long will that take? Okay, so you say you know that the vertical component of the velocity was initially equal to 10.71 meters per second. Okay. So basically, if we're trying to calculate how long it will take to reach the maximum height, well, we're trying to be figuring out how long will it take for this 10.71 meters per second to be reduced to 0, okay? And to do this, we're going to be using the kinematic equation, okay? The easiest one to use is, we could say Vf equals to Vi plus At. Okay, so you know Vf is 0 because the vertical velocity at the top of the flight is 0. So we're going to say 0 equals to initial velocity, you know, is 10.71, okay, plus At, okay. You know, acceleration of gravity is 9.8 meters per second, okay. But since it's acting in the opposite direction of the vertical velocity, okay, we're gonna say it's negative 9.8 meters per second, okay, because it's acting in the opposite direction. So the ball's going up while gravity is acting down, okay. So it's negative 9.8 meters per second. So the vertical velocity is being reduced by the gravity, okay. Let's say minus 9.8 t, okay? So if you rearrange to find t, you'll find that 10.71 divided by 9.8 equals to t, okay? So therefore, t equals to, plug that into your calculator, equals to 1.09 seconds, okay? You know that that the flight time is a parabola, okay? And you know in a parabola that the first half is symmetrical to the second half, okay? So therefore we can say that the total flight time, so basically 1.09 seconds is the time to get to the maximum height, which is half the flight time, okay? So if you multiply 1.09 by 2, we'll get the total flight time, okay? So we're going to say 1.09 times 2 equals to 2.18 seconds, and this is total time, okay? So now we know the horizontal component of the velocity, and we know the total flight time, okay? So we can simply say that range equals to horizontal velocity multiplied by time, okay? So range equals to it was 11.89 multiplied by 2.18, and that should give you plug this into our calculator. What does that give us? 25.92 meters. Yeah, equals to 25.92 meters. So therefore, the ball travels 25.92 meters before landing on the ground again, okay? And to get all the way to 25.92 meters, you're looking at an excellence grade, okay? If you get all the way to 25.92 meters, to get a merit grade, okay, you're looking at correct total time, okay? So if you find that t equals to 2.18 seconds, you're looking at a merit grade. And to get an achieved, you're looking at getting the correct half-time flight, okay? So you'll get the correct time for half the flight times, which is t equals to 1.09 seconds, you'll get an achieved. Alright, moving on. Question 2. Janet and Roy are ice skating. At one point, Roy is standing still. At one point, Roy is standing still, and Janet glides up to him from behind and grabs him by the shoulders. Janet's velocity as she glides up to Roy is 5 meters per second, and together they glide off at a velocity of 2.2 meters per second in the same direction as Janet was gliding. Assume that both Janet and Roy's skates are pointing in the direction of travel, okay? Roy has a mass of 65 kilograms, okay? State the law of physics that apply to this situation, okay? So basically, we have a theoretical collision, okay? And after the collision, okay, basically, there's an initial momentum of the system, okay? And after the collision, there's a final momentum, okay? So basically, we're gonna say conservation of momentum and initial momentum equals to final momentum, okay? So we're gonna say, we're just gonna say conservation of. Okay, and that's all you need, okay, to get an achieved grade, okay? Conservation of momentum will get you an achieved grade, okay? Alright, so calculate Janet's mass, okay? So basically, okay, we know that P equals to mv, and that the initial momentum is equal to the final momentum, okay? The initial momentum is equal to, okay, so Janet is gliding up at an unknown mass, but it's a known velocity, okay? So you know that the pi equals to, so Roy is standing still, okay? So basically Roy doesn't have any momentum, okay? Roy is standing still. So no matter how heavy Roy is, the momentum is still going to be 0. So let's say Roy is 1,000 kilograms. Okay, I know that's impossible. Let's just say Roy is 1,000 kilograms. P equals to mv. 1,000 times 0 is still 0, okay? So initial momentum is equal to an unknown mass, okay? So we're just going to say, we're just going to call it m, okay? So we're going to say 5m, okay? And then final momentum, okay? So the final momentum is equal to, the final momentum is equal to, so they start moving together, right? So when they start moving together, they have a combined mass, okay? So the combined mass, okay, that's 6, you know Roy is 65, and you don't know how heavy Janet is, okay? So you're going to say that, you know that the velocity is 2.2, so you're going to say final momentum is equal to 2.2 multiplied by 65 plus m, okay? Okay, so now we're gonna say that 5m is equal to 22.2 times 65 plus m, okay? So now we're gonna expand, okay? So we'll say 5m equals to, what's 2.2 times 60 equals to 143 plus 2.2m, okay? We're going to move the plus 2.2m to the other side of the equation. Plus 2.2 is going to become minus 2.2. Okay, so it's going to become 2.8m is equal to 143. And if you do 143 divided by 2.8, we should get 51.07. So therefore, we found out that the mass equals to 51.07 kilograms. Okay, so that's your final answer here. So mass equals to 51.07 kilograms, okay? So to get a merit grade, okay, you're looking at the correct answer for the mass, okay? And to get an achieved grade, okay, you're looking at recognition that a momentum is conserved. So you're looking at pi equals to pf, or you're looking for the correct, change in p, okay? So you're going to say, all states change in p equals 143. So you're looking at 143 here. That will get you an achieved. So any one of these will get you an achieved grade. Explain why you can use the assumptions you made while calculating Janet's mass, okay? So you know that they're ice skating, right? Okay. So when you're ice skating, there's pretty much just no friction on the ice, okay? We know that friction is an external force, okay? So because if there was friction, then the momentum wouldn't be conserved, because friction is an external force, and conservation of momentum only applies when there are no external forces, okay? So when you're on the ice, there's no friction, okay? It's a frictionless surface, okay? So when Janet collided into Roy, nothing was lost to friction, okay? So nothing was lost to heat and sound energy, so therefore their momentum was conserved, okay? So we're gonna say momentum is only conserved. It's only conserved when there are no external forces. When ice skating, we're gonna say that ice is a frictionless surface, and friction is a external force, and friction is an external force. Hence we assume conservation of momentum. Okay, so yes, this is a merit question. Okay, to get a merit question here, you're gonna have to say that the friction is the next. So basically, you're gonna say momentum is only conserved if there are no external forces, and you have to say that because they're skating on ice, there's no friction. Okay, and because there are no friction, we can assume the conservation of momentum. Okay. To get it achieved, okay, you're only stating that the momentum is conserved in no external forces, or you can say that ice is a frictionless surface and therefore the momentum is conserved. So any one of these 2 points will get you an achieved, okay? But to get a merit, you need both of these points, okay? Moving along. After removing her skates, Janet jumps down to the ground from a high bench. Write a comprehensive explanation of what Janet needs to do while landing so that she does not hurt herself. Use a formula to explain your answers, okay? Okay, so a good answer you have to think about, so what would you do, okay? So let's say you're jumping like, there's a really high ledge. Let's say it's about 3 meters high, okay? Maybe even more, let's say 5 meters high. So you want to jump down without hurting your knees, right? You don't want to hurt like your legs, okay? So how are you going to jump down? What are you going to do in order to not hurt your legs in this situation, okay? So you'll find that many people actually, they'll bend their knees, okay? They'll bend their knees when they land, okay? And the reason for this is it actually increases the stopping time, okay? So therefore, like, they have the same change in momentum, but if they bend their knees, okay, the same change in momentum is spread over a larger period of time. And because it's spread over a larger period of time, this means that the force experienced onto your legs is less, and because the force experienced onto your legs is less, then it's less likely to get injured, okay? So basically, just you have to imagine in a practical situation. So let's say you're jumping from a really high surface and you didn't and you forgot to bend your legs. Like normally that would hurt quite a lot, okay? That probably hurt your knees or hurt your legs, okay? But if you do bend your knees, you'll find that it actually softens the impact a lot, okay? So that's what you gotta say for this question, okay? So you're gonna say Janet. So we're going to say in order to increase to increase the stopping time, okay? To increase the stopping time, because the change in momentum is constant. It's constant whether or not she bends her knees. So because you know that if she bends her knees, or if she doesn't bend her knees, like she'll experience the same change in momentum. Like she starts from the same height above the ground, so therefore the change in momentum will be the same. Okay. It remains the same. Okay. So change in P is constant whether or not she bends her knees, and because change in P equals to force multiplied by change in time, and change in time has increased while the change in momentum has remained the same. We can say that change in P divided by change in time equals to force, and we'll just say and the same. No, that looks messy. And the same numerator divided by a higher denominator will give us a lower output. output, meaning less force experienced. Okay, so we're gonna link it back to why she won't hurt herself. Okay, so because there's less force, okay, she's less likely to get injured. Okay, so you're just gonna say therefore she is less likely to be. Okay, so that's your answer to this question. Okay, so to get an excellent question for to get an excellent answer for this, okay, you have to say that Janet has to bend her knees. Okay, and when she bends her knees, you have to say that it increases the stopping time. Okay, and when it increases stopping time, you have to say that the change in momentum is the same. Okay, so whether or not she bends her knees, the change in momentum is the same. Okay, and now you have to link it back to the formula. Okay, you got to link it back to change in p equals to f multiplied by change in time. You know that change in time is increased, but change in p has stayed the same. So you can rearrange the formula. You can say change in p divided by change in time equals to f. And because the p is the numerator and t is the denominator, the same numerator divided by a higher denominator will give us a lower output, okay? And this in terms, the output is force. So therefore, Janet will experience less force. And because she experiences less force, she is less likely to be injured. So you have to link all of these points up for excellence, okay? So that's all of these points linked for excellence. To get a merit, you're going to say that Janet needs to bend her knees, and you have to recognize that this increases the stopping time and reduces the force, okay? So you have to say increase stopping time and reducing the force, and Janet has to bend her knees, okay? So merit, and then to get an achieved, you're looking at only saying that Janet needs to bend her knees. So legit, you're just saying Janet needs to bend her knees, and that'll get you an achieved. So just legit, this line. That just gets you an achieved, okay? Alright, next question. When Janet jumps down, is her momentum conserved? Explain. Well, actually, no, okay? Her momentum is not conserved, and this is because gravity acts as an external force, okay? So like we remember what we just said before, conservation momentum is only assumed when we assume that there are no external forces acting. And because gravity is an external force, the momentum is not conserved, okay? So we're going to say her momentum is not conserved because gravity acts as an external force. Oh no. Okay, and that's all you need to say for an achieved. So this one line will get you an achieved grade, okay? Alright. Just gonna break it off here just in case my my thing decides to cut off again, alright?